Aloha, Richard Halverson here. This is ITS388AL, and we are in Chapter 7. I'd like to finish up the Chapter 7, discussion of Chapter 7 with this video. We're going to be covering extended addition and subtraction, and ASCII and unpacked decimal arithmetic, and also packed decimal arithmetic. So we're about here in the slides, and so let's just continue here. Extended addition and subtraction is a way of cascading words together or bytes together to make operands as long as you want them, as big as you want them, and so you successively add digits, just like you do when you manually do addition and subtraction. You do like a pair of digits at a time, and you start with the lowest order digits, and then you work your way to the left, adding each successive pair on top of digits that are one on top of the other, the addend on top and the augend at the bottom. And if there's a carry, you carry from one place to the next. And so basically you're doing the same thing. ASCII and unpacked decimal arithmetic is a way of more easily representing the digits of an operand in memory, and same with packed decimal. We'll get to that, but right now it's extended addition and subtraction. We're going to be using the ADC instruction, which is add with carry. It's how we do extended precision addition, and the SBB instruction is for subtract with borrow, is for extended subtraction, extended precision subtraction. And we do not, these instructions do not apply to 64-bit mode. So we're only talking 32-bit mode here. With extended precision addition, we are adding two operands that are longer than the computer's word size. So we're adding operands that are bigger than 32 bits, and it's usually some multiple of 32 bits. And when we do this, there's virtually no limit to the size of the operands. But the arithmetic must be performed in steps, just like we do with when we're doing addition by hand, and there may be a carry value that gets passed down to the next step. So when we so using the ADC instruction, the add with carry instruction is how we do adds. And so the instruction adds both a source operand and the contents of a carry flag with the destination operand, and the result is stored in the destination operand. So for example, how you would use it here, let's say you have two 32-bit integers, and let's say it's like, we're talking the largest integer that the word can store, and we're doing extended precision. So this top bit is not the top bit is not the carry bit. The carry bit is some place to the left in the uppermost word that's used for the operand. So this is just some really big number, and we're going to add, it takes up it's all ones in the lowest order word, and we're going to add another operand, a value that's also the same size, and we will be producing a 64-bit sum. So it's going to be the EAX register, which is 32 bits, and then is the lowest order, and the upper order will be the EDX register. So when we add these two, we have to start up by setting we better make sure we set the EDX to 0, because if there's any garbage up there, it'll be included in the result. So we move this large operand into EAX, and we add the same operand to EAX, and there will be a carry. And so the carry, the carry will be on the carry bit. And so I'm going to make sure I'm recording here. The carry will be in the carry bit, and then we do an ADC instruction, which is add with carry, and that will mean the result is so this here we're just adding 0 to the EDX register, but since we're doing ADC, then we're doing add with carry. So we're adding 0 plus the carry to the EDX register, which is already 0, and the result will be this 1 value in the EDX register. Hold on a second. Something's wrong with my pen. All right. So here's the same example. Add 1 to the EDX EAX register with a starting value of this. Oh, this is so we're starting a starting value of this, and we add 1, and we're adding 1. So we add the lower order bits first. So we're starting at, we zero that out. We set the lower half to this very large number, all ones, and then we add 1. We add the value 1 to it, and it's going to cause the EAX register to go to 0 because you add 1 to all Fs, and it wraps around, and a carry occurs, you know, out the carry flag, out into the carry flag, and then so with the carry flag set, we add 0 to EDX using add with carry, and we end up with this. The subtract with borrow is the same thing, except for where we're subtracting, and the carry bit is now the borrow bit, and so it subtracts the source subtracts both the source operand and the value of the carry flag from the destination operand. So so if the source operand is 5 and the destination operand is 10, normally 10 minus 5 would be 5, but if the carry flag is set, in other words, the borrow flag is set, then it's going to subtract 1 more, and it'll end up being 4. That's how we would do. That's how we would do subtraction by hand. So it's the same kind of thing as ADC instruction. So here, for example, we are. Let's say the value of EAX EDX is this. Subtract the lower 32 bits, setting the carry flag, and then we set the upper, and then we subtract the upper bits, which includes the carry flag. So here we're setting 1 into the EDX register, and that's how we end up with this here. Just a minute, my pen died again. Can't use my pen. Hold on a second. All right, if this happens again, I guess I just won't use it. Anyway, so we set the EDX register equal to 1, just like this. EDX is 1, and 0 in EAX. So it's 0 here. And so if we were to subtract 1, from this number, we should end up with all F's down here, and then there should be a borrow out of the EAX register. So I mean, a borrow out of the EDX register. So here we are subtracting, we subtract 1, and then we simply, so we do the lowest order first, and then we just simply subtract 0 from EDX, and the carry flag will be set, so because it's a borrow, because when we subtract 1 from all zeros, we have to borrow from the next highest order word or digit, and then when we subtract 0, we also subtract 0 from this. We also subtract out the carry, which is the borrow, and then that ends up being 0. And the result is the lowest order. The EAX register looks like this, and the 1 was subtracted out of the EDX register, the upper order digit. All right. You know, this also and because multiplication, you can actually do multiplication using shift add, and then it's easy using this extended arithmetic to do extended multiplication also. All right, so what's next? Now we're going to talk about a different way of representing numbers inside the computer, and it's the first we're going to talk about unpacked decimal arithmetic, unpacked ASCII and unpacked decimal, and the instructions that go along with unpacked. Well, these are all the instructions having to do with representing numbers using the hex, what looks like decimal arithmetic, but we're really using hex digits. So it's called binary coded decimal, and these are the instructions. There's for ASCII decimal, there's the ASCII. Let's see, add ASCII addition. What does it stand for? Adjust ASCII addition, adjust ASCII addition, adjust ASCII subtraction, adjust ASCII multiplication, and adjust ASCII division. And so for these, 1 digit occupies 1 byte. So if we have a 5-digit number, that's 5 bytes. And we're only using the lower nibble, the lower 4 bits, and it's going to be 0 through 9. And then there's no A. A is really 10. So what these adjust instructions do is if you're adding 5 plus 5, you're going to get A, and these adjust instructions will adjust that A into 1, 0, where 1 is in the next highest order digit, and so that would be in the next byte, and then the 0 would remain in the lower byte. So that's binary coded decimal. What packed decimal integers are is you're packing 2 decimal digits in 1 byte. So 55 decimal is 55 hex, and so you still don't use A, B, C, D, E, F, and you have these decimal adjust. These are decimal adjust addition and decimal adjust subtraction instructions, which after you do the operation, it will you use those instructions to convert the format, or convert the hex result into back into this binary coded or this packed decimal representation. So here's an example. This is binary coded decimal, and binary coded decimal BCD integers use 4 binary bits to represent each digit, and we're talking about unpacked. So each of these is a byte. 4 bytes. That's 1 32-bit word, 8888, and of course there's a lot of wasted bits because this 8 only requires the lowest 4 bits, 7 lowest 4 bits, and so on. So there's a lot of waste in here, but it's a lot easier because we don't have to go through this conversion of decimal coded numbers to binary, and then do operations in binary, and then convert back to decimal for displaying. So we don't have to do that. ASCII decimal is just like binary coded decimal, except for these are actually ASCII digits. And so this is the ASCII digit for 8, the ASCII representation for the character 8. This is for the character 7, character 6, character 5. And so with this, you are reading ASCII characters right from the keyboard and plopping them right into these bytes here. And with these ASCII adjust instructions, you can actually do your addition and do your subtractions and multiplications and divisions on these ASCII characters, and then we adjust them afterwards, and they're already they're back in ASCII format, and they can be displayed out directly. So if you want to make a simple calculator, this is the way to go, because you have plenty of memory these days. Doesn't matter if you're wasting all the space. The other thing is there can be loss. There can be precision loss when you're converting from binary to decimal and back. If you're doing everything in decimal, by using this ASCII coded decimal or binary coded decimal, you leave your numbers in decimal format. So you'll never get these conversion losses of precision that you sometimes see when you're doing a series of additions, and at the end the number ends up being something 0.9999999 instead of just the whole number. That's because there's loss in the conversion, and this is a way to avoid that. So we have this ASCII adjust after addition instruction. That's what that stands for. And it adjusts the binary result of an add or an add with carry instruction. And so you use add or add with carry on these ASCII characters, and then you do this ASCII adjust, and it brings it back to an ASCII character, a set of ASCII characters again. So for example, here we're adding 8 plus 2. So first let's load into and so we're going to use 16 bits. We're just going to use AX, and so we have to load 0 into the upper byte, and we're going to load an ASCII 8 into the lower byte, which is so AX now contains 0038 hex, which is the ASCII character for 8, for the number 8, the digit 8. And then we're going to add 0032H. That's what the ASCII 2 is, 0032. So if we add if we have 0038 plus 0032, we get this 006. We have 0038H. This is 8 plus 8 is A, and then 3 plus 3 is 6. So this is the result. This is what ends up in AX, okay? And then we do this ASCII adjust instruction, and it turns this 6A into 100 hex. And that's exactly what it should be. It should be 10. The result is 10. And then see because really 8 plus 2 is 10. Yeah, 8 plus 2 is 10. So, and we're doing 8 plus 2. So the result should be 100, but we aren't done yet because it's not ASCII yet. It's just binary coded decimal. So then we OR AX register with 3030, which sets the lower 2 bits of the upper nibble to 3, and it becomes ASCII 10. 31 and 30 is ASCII 10. So that's how ASCII adjust after addition works. And it's the same for ASCII adjust after subtraction. Here's an example of we want to take 8 and subtract 9 from it. And if you, this is not, you remember it's kind of like we've got, let's say we have 2, 8 minus 0, 9. The answer is 8 minus 9 is 9. Borrow a 1. This turns into 1. And then 1 minus 0 is 1. So the answer of 28 minus 9 is 19. So if we have an 8 and we want to subtract a 9, the answer should be 9 with a borrow of 1. So that's what that is. And then, so this carry flag will be set because the borrow will be set to 1. And we then do the ASCII adjust after subtraction, and it converts it into, it just converts it into this. And then, then we OR the lower byte with 30, and we get an ASCII 9 in AL. And ASCII adjust after multiplication is the same thing. So we have ASCII adjust, but it adjusts the binary result of a multiplication. The multiplication must have been performed on unpacked BCD numbers. So if we are dealing with ASCII, ASCII decimal arithmetic, we need to AND off the lower 2 bits of the upper nibble to turn it into just plain old unpacked decimal arithmetic, and that's easy. And so here for example, we're going to multiply 6 by 6. We're going to do 6 times 5. So we'll put 5 in the lower order B register, and we'll load 6 into the lower order A register, and then we multiply B by A, and the result is going to be 11. Or this result's supposed to be 11, but when we multiply this by this, we end up with this. Let's see, 5 times 6 is 30, and yeah, this is 30. 1E is 30. 31 is 1F, and 32 is 200. So this is this equals 30 hex in hex. Well, it's the value 30, but it's in hexadecimal format. And then we do this ASCII after multiplication, and it turns into 30. We still have to OR this, we would still have to OR this with 3030. I mean, yeah, 3030 to turn it into ASCII. And presumably, if these were ASCII, you would have to AND them with 11002, or actually 0000 would AND off the upper bits of the nibble and convert them to unpacked decimal. All right, and same with ASCII, except for it's ASCII just before division. You have to do the adjusting before you do the division, and then it converts them into the right kind of representation, where once the regular division is done, it'll end up being the correct result. So with division, we end up with a quotient and a remainder. So here we're gonna divide 37, divide the value 37. So 37 divided by 5 equals 7 with a remainder of 2, right? 7 with a remainder of 2. So first we're going to load the 37 into the A register. And so that's 30. This is unpacked decimal arithmetic. So it's not the ASCII version of it, it's the decimal version of it. And so which means the upper nibbles are 0 and not 3. And so that's the dividend. This is the dividend, and this is the divisor, and this is the quotient, and this is the remainder. And so the dividend is 37. And then we do this ASCII adjust before division, and it turns it into this. And when it's turned into that, and we divide that by 5, so we load the divisor into BL, and then we do the division, and we end up with 25 divided by 5 ends up being this number. And what this number is, AX is the upper AH is the remainder, and the lower AL is the quotient. Okay? So that's ASCII adjust before division. And then there's packed decimal arithmetic, and packed decimal arithmetic is just like we were talking about, except for we don't waste the upper nibble. We use the upper nibble for a digit, okay? So we aren't talking about ASCII anymore. We're just talking about decimal, and we're talking about and we call it packed because we pack 2 digits into 1 byte. So, for example, this big number here, 1 byte, 2 bytes, 3 bytes, 4 bytes, see. And so you're able to do you know, addition and subtraction using packed decimal. We are able to do addition and subtraction using this packed decimal format. And there's a decimal adjust after addition instruction. And there's a decimal adjust, and this is the logic of it. So you want to understand exactly what's going on underneath. Here's some examples, and see these are packed decimal 35 plus 48. You add 35 and 48, and you get something. And then you do this decimal adjust after addition, and it converts it into what the packed decimal would be for what 35 plus 48 should be, which is 83. Here's an example of the second one. We're doing 35 plus 65, and we're going to end up with something called 100. It's going to be 100. 35 plus 65 equals 100. And so that's going to take up more bytes. It's going to take up 2 bytes. And so once we add, we end up with this. And then we do decimal adjust after addition. And the lower order ends up being 0. And there's a carry. So the carry is we just add 0 to the next byte, and a 1 will end up in the next byte. Here's an example of 69 plus 29. 8 plus 1 is 98, huh? Okay, yeah, that's right. All right, so and decimal adjust after subtraction, same thing. And we are, so carry flag represents the borrow, and so we don't have any examples of here where the borrow is set. But anyway, you can see how this works. It's as you'd expect. And some more examples here. So So in this chapter, we began, if you remember, talking about shift and rotate instructions, and then we covered the multiplication and division instructions, and these were to extend, to convert like a byte operand to a word operand, or convert a double word operand into a quad word operand, and so on, to um, extending the sign, close relatives of shift left and shift right, because they're sign extended, and then at the end we learned about this uh, extended precision, how to do extended precision arithmetic using the add, carry, and add and subtract, borrow instructions, and then how to do ASCII decimal operations and binary coded decimal operations using these instructions, the ASCII adjust after addition, ASCII adjust after subtraction, multiplication, and ASCII adjust before division. And then finally, the packed decimal operations, which pack two decimal digits into 1 byte. All right, so that pretty much finishes up chapter 7. And so you know enough from the last video to do the assignment. And next week we will start with chapter 8. Thanks for watching.